All right, let's talk about the invisible world around us. Specifically, the powerful forces that fluids, like air and water, are constantly pushing and pulling with. These forces shape, well, just about everything in ways you might not even realize. And it all starts with a feeling I bet you know really well.
You've done this, right? You stick your hand out the window of a moving car, and you can literally feel the air. You can feel it pushing back on your palm. And if you angle your hand just right, it lifts up like an airplane wing. Or you can cup it, and suddenly it feels like something is yanking your whole arm backward. That push, that lift, that's the fluid, in this case the air, making itself known. Well, that backward yank has a scientific name. It's called drag. And simply put, it's the force that a moving fluid pushes on an object with. It's the main thing that tries to slow everything down. For anything that has to move through air or water, from a Formula One car to a jetliner, understanding and beating drag is the entire game. But here's the thing. This force we call drag isn't just one single thing. Nope. It's actually the combination of two totally different things happening at the same time, all over an object's surface. So let's break down these two faces of drag. Okay, so on one hand, you've got friction drag, and that's pretty much what it sounds like. It's the fluid literally rubbing along the surface of the object, kind of like a sticky shear force. If you imagine a super thin plate held perfectly parallel to the wind, almost all the drag it feels is just that friction. Now, on the other hand, you have pressure drag. This one's all about the object's shape. It's caused by the fluid basically crashing into the front of the object, which creates high pressure, and then leaving a big, empty, low-pressure space behind it. So if you take that same flat plate and turn it to face the wind, bam, almost all the drag is now pressure drag. So we've got two kinds of drag, but the plot thickens, because the fluid itself can have two very different personalities. It can be super smooth and orderly, or it can be a total chaotic mess. And which personality it has, well, that has a massive impact on drag. We call these two personalities laminar and turbulent. Laminar flow is the smooth one. You can picture it as these neat parallel layers of fluids sliding past each other. Turbulent flow is its wild, chaotic sibling. It's a mess of swirling eddies and intense mixing. Now, you'd probably assume that smooth, laminar flow is always better, right? I mean, all that chaotic mixing in turbulent flow just seems like it would create way more friction against the surface. And you'd be right about that, mostly. So what makes a flow decide to be smooth or chaotic? Is it just random? Not at all. There's a rule. The switch from smooth to chaotic is actually governed by a single, critical, magic number that can predict the exact moment the flow will trip from being nice and orderly into total turbulence.
And here it is. It's called the Reynolds number. You can think of it as a cosmic tug of war. On one side is the fluid's own internal stickiness, its viscosity, which wants to keep everything smooth. On the other side is the fluid's momentum, its speed and energy, which is trying to tear it all apart. The Reynolds number is just the score in that battle. And for flow over something like a flat plate, once that score hits about 500,000, momentum wins. The flow just can't hold it together anymore, and it trips from smooth laminar into chaotic turbulence. It is a fundamental tipping point in how fluids behave.
Okay, let's put all this together now to solve a classic puzzle. Based on everything we've just talked about, it really seems like smooth laminar flow should be the goal for cutting down drag, doesn't it? Well, if that's true, let's take a look at an object that's literally designed to fly through the air with as little drag as possible, a golf ball. And here's the paradox. This is what's so weird. If smooth flow is good, and we know that turbulence creates more friction, then why on earth are golf balls covered in dimples? Why aren't they polished to a perfect, mirror-like shine to encourage that nice, smooth, laminar flow? The answer, it turns out, is one of the coolest and most counterintuitive tricks in all of engineering. So, let's first imagine a perfectly smooth ball. As the air flows over its front surface, the flow is laminar, just like we'd expect. But that smooth flow, it's kind of low energy. It doesn't have the oomph to stick to the ball's surface as it curves around to the back.
so it separates from the surface way too early. And this creates a huge, turbulent, low-pressure zone behind the ball. We call that a wake. It's like a giant vacuum bubble sucking the ball backward, creating a ton of pressure drag.
And the numbers here tell an absolutely wild story. At the speed of a good golf drive, a smooth sphere has a drag coefficient of about 0.5. But a rough, dimpled sphere at the same speed, its drag coefficient plummets to just 0.1. That means making the ball rough reduces its drag to just 1/5 of what it was before. How is that even possible? Here is the brilliant trick. The dimples are there on purpose to trip that smooth, low-energy flow into a chaotic, but much more energetic, turbulent flow, right at the surface of the ball. This new turbulent layer has so much more momentum that it can hug the curve of the ball for much longer before it finally separates. And by delaying that separation, the dimples make that low-pressure wake behind the ball shrink a lot. So it's a trade-off. You're accepting a tiny increase in friction drag in exchange for a massive reduction in pressure drag. And for a golf ball, that is a trade that lets it fly hundreds of yards farther. It's an absolute game changer.
So this idea of controlling how a fluid behaves right at the surface is incredibly powerful. But its importance doesn't just stop with drag. There is another huge area of physics that is governed by these exact same principles: heat transfer.
There's a really deep connection here, and the source material puts it perfectly. The phenomena that affect drag are the very same ones that affect heat transfer. What that means is the way a fluid pushes on an object is directly tied to how well it can cool down or heat up that same object. Here's how it all connects. We know that the flow's personality, laminar or turbulent, determines the drag. Well, that exact same personality also determines how quickly heat moves. Think about it, that intense, chaotic mixing in a turbulent flow. The same thing that increases friction drag also makes it amazing at grabbing heat from a surface and carrying it away. So by learning how to control that thin layer of fluid, engineers can suddenly control two critical things at once: aerodynamics and thermal management. And this isn't just theory. This idea is at the heart of so much of our technology. It's how we design the cooling systems in our cars. It's essential for the giant heat exchangers and power plants. It even explains something as simple as why a steam pipe loses more heat on a windy day. If you can master the flow, you can master both force and heat. So, the next time you stick your hand out of that car window, or you watch a golf ball just soar through the air, remember what you're really seeing. You're witnessing this beautiful, complex, and totally invisible dance between an object and a fluid. It's a dance that engineers have figured out how to choreograph, all to make our world work a little bit better. Thanks for joining me on this explainer.